our today's speaker, Joshi Chikamoto from Utah State University. Joshi is an assistant professor since 2017 at USU. And his research background or specialty is on climate predictability, maybe resulting from air-sea interaction, low frequency sea surface temperature variations. He's also interested in phenomena like ENSO and I guess the PDO, Pacific Decadal Oscillation, and what all this does to our water supply here over North America. And he has actually a couple of very interesting high-profile papers on that topic, if somebody is interested on this. And yeah, and so today he's going to talk to us on, again, atmospheric predictability with respect to the stream flow of the Colorado River, resulting from dynamical models. And yeah, with this, I hand over to Joshi and look forward to see what you have to say.
Yeah. Thank you, Thomas. So I just try share screen. Here we go. So does it look okay?
Looks very good.
Okay, so okay, thanks, Thomas. So I'm Yoshi Chikamoto, assistant professor at Utah State University. So first of all, thank you for inviting me in this seminar, Department of Atmospheric Science, University of Utah. So actually, I'm very excited to share our recent research with you because we are living pretty close, but I have not so much chance to collaborate with members in Utah, University of Utah. So I hope this is a good start to make more close collaboration with you. So today's talk, I want to talk about multi-year predictability of Colorado River water supply, which is mainly driven by remote ocean impact. And this study is I want to acknowledge my colleagues, Simon Wang, Robert Gio, Matthias, and Larissa Yukon. So this paper, today I want to talk about this topic. But before I talk about research, first I want to briefly introduce of my career. Oh, and by the way, if I have a question, please let me know anytime, and then feel free to jump in and start discussion. So this is a global map, and my journey starts from Hokkaido University in here, northern part of Japan, when I was a graduate student. And I got a PhD in 2005. And then my topic, research topic, is atmosphere-ocean interactions. And after I got a PhD, oh, yeah, by the way, Hokkaido University is looks like here. And there's a lot of mountain and snow, and snow is a powder snow, and there's a lot of ski resorts. So Utah is pretty similar climate in Hokkaido, northern part of Japan. And after I graduated, I moved to the Kyoto University almost 1 year, talking about research about MJO predictability, Madden-Julian oscillation. And after that, I joined the 5-year research project in University of Tokyo, working about decadal climate prediction. And then this research contributed to the IPCC fifth assessment report in chapter 11, near-term predictions. And then I learned a lot of climate modeling and dynamics when I was here. And then my research is mainly focused on the tropical climate, but I have never lived in the tropics. So after this 5-year project, I decided to move to the tropical climate, which is Hawaii. So I work in the University of Hawaii with Professor Axel Timmerman. research topic is decadal hydroclimate predictability, and I spent there for the 5 years. So it's a pretty nice tropical climate, pretty warm. Every time it's kind of spring, and it's have a nice beach. So I can feel tropical climate a lot. And after that, I moved to the Utah State University from 2017 as an assistant professor. And my research is kind of continuous from the previous work, but try to advance more dynamics and then also make a lot of collaborations to do more wide variety of climate prediction, or we call Earth system predictability. So through my journey, research journey, what I learned is we are living one world. Of course, we are living in one world. But what I feel is we have really global connections. This is pretty important. Every global is connecting. And today's my talk, we will see how global is connected and why it is important. But anyway, this is my brief introduction. And then this is today's topic. So first, I want to introduce drought impact on agriculture and forestry in the Utah on the Intermountain West. And after that, I want to show you a result about decadal prediction using a dynamical model. And then after that, I want to talk about ocean precasters, and last part is application. So again, if I have a question, please let me know anytime, and you can jump in or you can put the chat. So I try to keep an eye in chat. So feel free to join. Okay, but anyway, let's start introduction. So this is a time series of natural annual mean Colorado River water supply provided by Bureau of Reclamation from 1960 to 2018. And this natural streamfall is measured by Lee's Ferry, Arizona, in here. And we can see water supplies have an up and down in year-to-year variability. And then some year we have water shortages, and these water shortages correspond to the drought years. And as you know, if we have a drought, we have a lot of problem in the Intermountain West. And particularly so severe drought is pretty major concern for us. So first, I want to show you how this kind of drought affect to our agriculture and forestry in the Intermountain West. So this is another time series of annual crop yield based on the vary from 1960 to recent years over the Intermountain West. So this time series normalized by value in the 1960, so about 100%, and the y-axis is a logarithm. So you can see increase of this annual crop yield based on the vary, and this is indicate its exponential growth of this crop production because this is a logarithm. And then if we check other crop like corn or spring wheat or winter wheat or alfalfa, all of them show the increasing trend. So there's kind of exponential increasing trend. So, and this kind of trend, increasing trend, is driven by technological advance. So our agriculture technology is getting better, so we can have exponential growth of production. But if we close look at this time series, sometimes we have reduction of a crop. And if you overlay the drought year, we can see during the drought year, many crops tend to have reduction, like here, here, even though we have an increase of the crop yield production due to the technological advance. So, and then this is another indicative drought may be affect to the crop failures. So to highlight this drought impact, I just remove linear trend from all of them and average 5 crops. And this is this green lines. So then some year we have crop reductions. And then I remove the trend, so it's not trend. And if I overlay Colorado River water supply, like this blue line, we can see that highly correlate each other. So during the drought year, we have crop failures. And if I overlay the wildfire intensity over the Mountain West, this is kind of opposite phase. So during the drought year, wildfire intensity become more stronger. And during the wet year, it's become weaker. And this is a correlation between blue line and green line, or blue line between red line. So based on this correlation also suggests water supply is relating to the wildfire intensity and crop failures. I want to show you another way how drought affects the agriculture and wildfire. So this is a probability distribution or histogram based on the Intermountain West area. And this left panel is the soil moisture, crop yield, and the right panel is wildfire intensity. And this is a log scale. So slightly different, but anyway. And then all of them, if we include all years, we can see normal distributions. Okay. And from this time series, when I pick up drought years and then make a same PDF like this, red colors, and then we can see during the dry years or drought years, soil moisture become more drier in the many region, and the crop show the failure, and the wildfire become more active and intense wildfire. So this is another way to show water supply variability is related to the drought conditions, crop failures, and fire activities. In other words, if we can predict this water supply in the future, we can also assess how much crop may fail and how much fire danger will increase. So my main topic of this research, or main question is, can we predict this water supply variability in the future? And my answer is also, I want to say yes. But if I say yes, another question is, how long can we predict, and why can we predict it? Of course, this is really challenging, but you will see how we overcome this challenging topic using some hypotheses or assumptions. Okay, so I want to introduce hypothesis based on the schematic view in here. So let's think about atmospheric variability. And atmosphere include weather disturbance, and typically speaking, weather disturbance is more short time scales. So variability is really high frequency. But atmosphere also have long-term trend due to the radiative forcing, like greenhouse gas increase or volcanic eruptions. And atmospheric variability also include lower frequency interannual to decadal variability, and mostly these are driven by ocean forcing or atmosphere-ocean interactions. So in the atmosphere include all of these time scales. And then as a result, if we check the spectrum in the atmosphere, typically it shows white noise. And this kind of white noise behavior or random behavior affect the RAD processes, and some feedback from the RAD But these kind of random variability affect the land process, and then land response to the atmosphere is typically like more white noise. But if we check, if we see some variables like soil moisture or stream flow or tree growth, those are pretty slow variability. And then those are pretty slow variability. And the reason why these sometimes they show the slow variability or low frequency variability might be this atmospheric high frequency component will be the filter out due to the land process. So I call this is a coffee filtering effect. So let's think about to make a cup of coffee using a drop coffee. Okay. So if you pour hot water from top, but this pouring hot water may be the kind of random. Water, no water, water, no water, like a rainfall, precipitation, kind of random. And then sometimes you can do the high frequency. But if we focus on the output from this filter, that one also shows low frequency. So even though input is random, output should be the low frequency due to the filtering effect. And then my hypothesis is some land process acting like this coffee filtering effect. As a result, this high frequency component becomes filtered out, and then only this low frequency component affects the land processes. And the low frequency variability basically originates from low frequency ocean component. So I call this the ocean memory. So as a result, we may find low frequency component, a coherent variability of the low frequency component between ocean and some land process like a stream flow variability. So this is my hypothesis, and then our hypothesis, and then based on this hypothesis, I want to show how low frequency ocean variability contribute to the low frequency stream flow, and how can we predict it. Okay. So that was the introduction, and then if you don't have any questions, I want to move to our dynamical prediction. Okay. So in here, we use a decadal climate prediction system, and then climate model we use is a CSM, NGA model, Community Earth System model. And this CSM have 4 components: atmosphere, ocean, sea ice, and land. And these 4 model components are interacting each other through the coupler. And this model also have radiative forcing like a CO2 increase, or volcanic eruption, solar variability. And then they try to simulate long-term climate change. And in our hypothesis, we assume low frequency ocean component will be the important to drive land variability. So what we did is we tried to put observed ocean information into the ocean model component in the CSM based on the data assimilation technique. So this ocean part in the climate model is pretty follow with observed ocean variability like El Nino, La Nina, or PDO. But in this model also has other components like atmosphere and the land. So if our hypothesis is really true, if this data assimilation approach can simulate observed land variability if ocean is important. So we try to run this ocean data assimilation from 1960 to 2012 or something, like 50 or 60 years. And then we get the ocean data assimilation experiment. And then from this ocean data assimilation experiment, we pick up initial conditions every year, and we conducted a 10-year a hindcast experiment. So this procedure is pretty similar to like a weather forecast. So using the data simulation technique, we get a model initial conditions and then try to run the model filter for the forecast. But with the forecast is only atomic model, but we use a couple model, and the main memory is coming from ocean observation. And then we conducted this hindcast experiment based on the 10 ensemble members, and the ocean data simulation, we also have 10 ensemble members. And then by analyzing the hindcast experiment, we can assess how long we can predict a random component like stream flow variability. There are a lot of technical details in this system, and if you are interested in, we have another paper, so you may refer to this paper. But anyway, this is our model experiment. And again, point is in our model, we prescribe observed ocean information, but there's no atmospheric observation, no random observation. And we try to see the coherent variability between our model simulation and observation. Okay. So this is the result. But this is still observed Colorado River water supply, as I showed in the introduction. And then for the model, they don't have any river stream flow. So we somehow need to reconstruct Colorado River water supply based on the defined variables that one model had. So this is a correlation between soil moisture anomalies in the NCEP reanalysis with this observed Colorado River water supply, this blue line. And we can see the highly correlated over the Mountain West. So that means if water supply becomes shortage, we can see the dry soil conditions. And if we have large amount of water supply, we can see pretty wet soil conditions. And if I try regional average of soil moisture in this black box region, that one is this dotted line, we can see that highly correlated each other. So in other words, if we have a soil moisture, we can reconstruct Colorado River water supply by taking the regional average. So we have applied same method to model simulation, and this is our result. So this is a ocean data simulation run. Using the ocean data simulation run, we try correlation between model simulated soil moisture anomalies with observed Colorado River water supply. And we use a lower resolution because it's computational cost, computationally expensive. And the model still have biases, but model try to capture positive correlation around the Utah area. And if I take regional average of soil moisture in the model, that one is this solid black line. And then we can see highly coherence between observed water supply and our model simulated soil moisture variability. So this is pretty interesting because our model simulation, we only prescribe observed ocean information. And the model doesn't have any atmospheric observation, any land observations, but a model land variability tend to show coherent variability with observations. So this is another kind of evidence to support our hypothesis. So this is suggests ocean can derive low frequency variability of stream flow if we include observed ocean information into the model. And then so this is the annual mean basis, and the correlation is 0.43 with the observation and our model simulation. But if we apply low pass filter, this correlation become more higher. So our model tried to capture low frequency variability of coral river stream flow. Okay, so based on this result, we tried to assess predictive skills of water supply. So this is the same time series and the same with before. Black solid line is a model of ocean data assimilation line, model simulation. And dotted line is a reconstruction based on the reanalysis soil moisture data. And then those are highly correlated. And the right panel shows the predictive skills based on the anomaly correlation coefficient. So if anomaly correlation become high, that means the skill is high. And then x-axis is the lead time, and the skill is getting lower due to the lead time. And then this dotted line is a significance level. So if value become more higher than this dotted line, we can say result is statistically significant. And this black line shows the persistent forecast. So persistent forecast is pretty simple. From the initial value, you just do the same values continuously with the forecast. If we start from here, next forecast is same value, same value, same values. So it's kind of nothing special. And then according to this persistence, they have some autocorrelations. Okay? And then if our model prediction is lower than these skills, that means a model is useless. But if a model scale become more larger than this black line, that means a model have some important information. So this is kind of benchmark, and we want to overcome these persistent skills. Okay, so let's see the result. Okay, so this blue line is a component coming from external forcing, or in other words, it's coming from greenhouse gas information, like climate change component. And the climate change component is pretty low. So this is a predictive scale. So climate change has no impact to these scales, and we can see more large decadal like variability. So coral river water supply is mainly driven by low frequency component, not the external forcing. So climate change component is negligible. And this
Actually, I have a quick question.
Yeah.
Sorry.
How
do you determine this external forcing only? That was a specific simulation, a specific run?
Oh yeah, sure. So I forget to explain, but it's only prescribed external forcing, like historical run. And then no data assimilation, so it's model free run. And we have 10 ensemble members.
Okay, thank you.
Yeah, so yeah, it's only prescribed historical run, yeah. Like IPCC report. Okay, and then this red dot is our hind gas experiment initialized based on the ocean information. And then this red dot is a 1 year forecast, and then circle is ensemble mean, and then bar is ensemble spread. And if you follow this red dot, it just track, observes coral river water supply very well. So this red solid line is a hind gas scale between this red circle and CPC soil moisture reanalysis data set. And according to these skills, we can see like 36 months, so like 3 years, they have a skillful prediction. And if we compare with this red circle and black solid lines, the model simulation, skill is much more higher. So this is kind of upper limit or potential predictive skills in current our model currently have. And this red solid line is more practical skills. But even though these practical skills, we may have a skillful result up to the 36, like 3 years in advance. So this result string support Colorado River water supply is predictable for several years. So this is just a dynamics of model result, but we still don't know what is the mechanism underlay in this phenomenon. So I want to try to discuss what is the driving force of these predictive skills. So to check dynamical component, I made composite analysis during the dry years or shortage years based on the water supply. And the contour line indicates 500 hectopascal geopotential height, and the shade over the land indicates soil moisture anomalies. And the left panel is a reanalysis data set. Middle panel is our simulation run, and the right panel is a 1-year handcast run. So this is a shortage year, and then we can see some high pressure in observation and dry conditions. And the model may also try to have drier conditions, but it's not so significant. But if we go back to 1 year, 1 year before the shortage, here we go. This is 1 year before the shortage. We can still see high pressure system over the United States. And we can see the dry soil conditions over there. And we can also see some high pressure, low pressure, high pressure pattern in the North Pacific. And if you go to 2 years before the shortage, we can also still see high pressure, low pressure, high pressure system in the model, in observation. And the model also tend to have dry conditions over the United States. So there is some time lag between observation and our model, but dynamics sounds like similar. So this atmospheric large scale circulation can drive dry soil conditions, and that one contribute to Colorado River water supply.
Yoshi, what time of year do these represent, or do they represent a specific time of year?
Oh yeah, thanks. So this year is based on dry years from this time series. So 1, 2, 3, 4, 5, 6, 7 years. And then just make a composite. Does it make sense?
Yeah, thank you.
Yeah. And then just go back from the dry year. So this is an indicative of dry or water shortage in Colorado River. Yeah, thanks. So our dynamical model tend to show water shortage, and that one related to the large scale atmospheric circulation. But again, our hypothesis is those water shortage is driven by ocean conditions. So by tracing back to the past based on our model, we can find ocean precursors that one can drive a water shortage of Colorado River. So from here, let's try to find what is the ocean conditions important for drought conditions in the Colorado River. Okay, so to find the condition, I want to make a scatter plot. So this scatter plot, x-axis is observed Colorado River water supply, and the y-axis is a model reconstructed or model simulated Colorado River water supply estimated from soil moisture variability. And each dot shows each year. So again, this is a positive correlation. So that means a model tends to capture water shortage, observed water shortage. And the point is this lower left quadrant. So in this quadrant, observations show dry or water shortage, drought conditions. And our model also shows the drought conditions. So this quadrant indicate our model can capture drought years, and these years may be driven by ocean component. So we pick up 1, 2, 3, 4, 5, 6, 7, 8 years, predictable years, and then by tracing these 8 years, what kind of ocean condition, and then we can try to find ocean precursors. And this is the sea surface temperature anomalies for simultaneous short water shortage years. And we can see some warming in here, but it's nothing special. But if we go back to 1 year before the water shortage, we can see the La Nina-like pattern in the tropical Pacific. And if we go back 2 years before the water shortage, we can see the sea surface temperature warming in the North Pacific. And then we can go back to 3 years before the shortage. We can also find sea surface temperature warming in the tropical Atlantic. So these results suggest these ocean conditions is kind of precursors for water shortage of Colorado River water supply. So let's try to see again how does it look like in the atmospheric circulation. In here, contour indicate 500 hectopascal geopotential height anomalies, and the color show the sea surface temperature anomalies. And the left panel is kind of the analysis or observation, and the right panel show our ocean data simulation run. So during the water shortage year, we can see high pressure, and then temperature is warming in SSD warming in here, but it's like looks like nothing special. But if you go back to 1 year before the shortage, we can see the La Nina-like pattern, and we can see significant high pressure, low pressure, high pressure, high pressure, low pressure, high pressure pattern. And this high pressure over the United States, that one contribute to dry conditions.
Yoshi, the atmospheric conditions here, is that for the whole year? All
Yeah,
months of the year?
sure. This is annual mean. Yeah.
Okay.
Yeah. So we didn't specify any season, so we try annual mean.
I guess maybe I'll ask my question now. Is there a reason to focus more on the time during the snowfall? Because that's when a lot of the precip happens, right? Are you averaging in months that are not as relevant?
Yeah, so
for the Colorado River.
Yeah, it's a really good question. So we need to do the next. Yeah, so far we just only focus on annual mean to filter out high frequency atmospheric component. Yeah, but I totally agree. Snowpack or during the winter season, that will also important. So we also need to carefully check what the seasonal impact. Yeah, it's really good. But so far, we just only see the annual mean, so no seasonality.
Okay, thanks.
And then if we go back to 2 years before, we can still see high pressure, low pressure, high pressure system. And we can also see the North Pacific SSD sea surface temperature warming. And if you go back to 3 years before the shortage, we can see the Atlantic warming, and then observations show more high pressure, low pressure, high pressure system. And the model only shows here, but that may be the driving force of the drought condition over the United States. So this is also kind of consistent tropical Atlantic and North Pacific and the tropical Pacific. Those might be the important precursors. But questions still remain. Usually people focus on tropical Pacific and maybe North Pacific because it's pretty close to the United States. And then atmospheric circulation can propagate like from west to east. So that doesn't make sense. But tropical Atlantic condition is still kind of questionable why we need to take care about tropical Atlantic. And the reason is coming from recent research about tropical inter-basin interaction. So this is a schematic view of a tropical inter-basin interaction we call tropical trans-basin variability. So in the trans-basin variability, point is Pacific and the tropical Pacific and tropical Atlantic sea surface temperature anomalies. Those are opposite phase. So during the positive phase of trans-basin variability, we can see the El Nino-like warming in the Pacific, but Atlantic shows a cooling. So it's a strong contrast. And during the negative phase, we can see the La Nina-like pattern in the Pacific, but Atlantic shows a warming, so opposite phase. And this opposite phase is kind of interacting, and then through the global Walker circulation, and then connecting each other. And the point of this interaction is the time scales. So Pacific looks like El Nino-like pattern, and then this is a path spectrum of the El Nino in blue line, and that one typically like a 4 to 5 years. But if we focus on trans-basin variability, it's more like a wide, and the interaction between Pacific and Atlantic, like a seesaw. That one shows a path spectrum peak at decadal timescales. So that one is more lower frequency. And if lower frequency component if we found, that maybe contribute to more long-term climate predictability. So actually, if I try to plot precipitation anomalies and the soil moisture anomalies associated with positive and negative phase, we can see during the positive phase, this is a long-term winter. After 1 year later, we can see the North United States tend to have more wet conditions. And if you have a negative phase of tropical trans-basin variability, we can see more dry conditions after the this phase 1 year later, after the peak of trans-basin variability. So Colorado River water supply prediction is also have a similar concept or consistent with this climate phenomenon. So Atlantic is also another key area to predict dry condition over the United States, Western US. Okay, so we found that ocean precursors, and using ocean precursors, we can try or we can apply to develop multi-year forecast of Colorado River water supply. So I want to show you this component in this slide. So this is a summary of what we found in the ocean memory. So we found tropical Pacific cooling 1 year before the shortage, and SST warming in the North Pacific 2 years. 2 years before the shortage, and the tropical Atlantic sea surface temperature warming 3 years before the shortage. So point is, if we monitor this sea surface temperature variability, we can develop multiple regression, and we can try to develop forecast model to predict Colorado River water supply. So point is monitoring this sea surface temperature, and then this is a kind of multi-regression coefficient, and using this equation, we can produce, or we can try the forecast of Colorado River water supply. And then this is the result. So color shows the observed Colorado River water supply, and our black line shows the predictions. And the correlation between our prediction and water supply observation is 0.62, so it's very high. So using this system, we can, it's pretty simple because we just only monitor the sea surface temperature anomalies, and we can try to assess future water conditions. So based on this system, we developed a monitoring site. So, and then we have some update. And what we found is if we focusing on or monitoring the sea surface temperature warming in the North Pacific and the North Atlantic, we can produce forecast. So this blue line is our observed Colorado River water supply, and the red line is our forecast based on ocean precursors. And then thin line is annual mean, water year means based, and this thick line is a 3 year running mean filter, so more low frequency. And as you can see, water supply and our forecast show the really highly coherent each other. So correlation is really high, particularly for low frequency component. So our concept or hypothesis is kind of reasonable. And then based on this monitoring equation, we can try to assess future conditions. But the question still remains, how does it look like in this year or next water years? Do we still have shortage or we have recovery or not? So if we are interested in, we have a web page. Oops. So web page in here. If we go to the Utah Climate Center web page, forecast, we have Colorado River water supply forecast, and then we have a web page updated in this here. And according to our forecast, 2023, 2022, and the 2023 water year getting lower. So according to the current water conditions, future water supply may be decreasing, so more serious drought may be coming. So we need to be careful. It's not good for us. But anyway, this monitoring site will be updated every year, like summer. And then if you're interested in, you can check this webpage. And if you have any suggestions, please feel free to email me so we can see how does it look like. Okay, anyway. Here we go. So this is a conclusion or kind of summary. So we try to predict Colorado River water supply year-to-year variability. And our model suggests we can predict Colorado River water supply for several years in advance by utilizing ocean memory and also a land filtering effect. And we try to assess this scale based on the dynamical prediction and also ocean precasters. And these two components support our hypothesis. So ocean is one of the important driver for long-term drought conditions over the Colorado River. And again, we are living in Utah. So if you want to see the Colorado River, you may only care about Upper Colorado River region. But our results suggest Colorado River water supply is also connected to the global sea surface temperature pattern. So we can see the global connections. So point is, this is just a start. And then it is kind of minimum requirement. So if we advance our model or dynamics or understanding, we may provide more long-term predictabilities and more high. We can try to improve predictive skills much better. And of course, there are a lot of questions. How does it look like in the winter or summer? How does it connect to local hydrological conditions? So we still need to work a lot. But at least there are some hope to predict Colorado River water supply for several years in advance by utilizing the ocean information. Okay, so this is the final figure slide. So thank you for your attention again. Today's topic is published in the new Nature Journal Communications, Earth and Environment, and you can see right here. And I also have some comment about this paper. So if you are interested in, I really appreciate to download and read it. And if you have a question or comment, feel free to contact me. So collaboration is really welcome. And then this is my email address. We are living pretty close. So if you have any idea, feel free to contact me. Anyway, That's it.
Okay, thank you, Yoshi, for this very interesting talk. So I open it up now for questions.
Mhm.
Anybody want to have a question?
I was wondering, Yoshi, it looks like on your data around 2016, there's a pretty big divergence from the prediction and the observed. Was there anything unique in the input data that year that might explain that?
So 20.
That was on that last graph that you had up.
Also, maybe the web page might be better.
Yeah, there you go. Yeah, it looks like around 2016, there's a pretty big divergence there.
Yeah, I see. Yeah. Good question. So don't know. So one component might be a model try to predict only ocean-driven part, and the atomic randomness doesn't calculate within here. So one kind of possibility is atomic randomness prefer more dry conditions. So that one just only the unlucky, maybe. Another component is a model is just simply linear regression model. And then what I tune is I try to assess dry conditions, not the wet conditions. So wet condition may be disadvantage, or there are some other mechanisms to drive wet condition over the Colorado River, like a non-linearity. So yeah, it's a really good question. I think I didn't answer correctly, but this is what I'm thinking. Yeah. So yeah, pretty interesting one in here.
Jim, did you have a question?
No, it's okay. I got it from the previous one. Thanks.
Are there any other questions?
I have a quick question. I just was wondering, how long do you just plan on like continuously doing this data? Obviously, what trends do you expect to see within the next 20 years, if you can just take a guess?
Yeah, so it's a really good question. So if we only use the ocean precursors, we cannot do more longer. Okay, but if we can try dynamical predictions, we may do it. But according to our result, dynamical prediction still kind of skillful up to 36 months. So if we go extend more like 5 years or 10 years, our model prediction merge to the like climatology or external host component. So in the case, information is not used for that one, only coming from climate change component, ocean memory doesn't work. So yeah, so far, according to our current result, it's only 3 years. This is our current maximum. Does this sound good?
Yeah, thank you.
Yeah.
Awesome.
Let me see in the chat. There's something. Okay. Somebody's asking, thanks for an interesting and informative talk. With this approach, are you able to account for factors like changes to warm season evapotranspiration or changes in delivery of wintertime precipitation, changing from snow to rain at some elevations?
Yeah, so it's a very great question. So what we try to do next is, again, so this is, we only focus on the annual mean, and we need to think about seasonal component. And then one of the good news for us is we found the ocean precursors. So based on these ocean precursors, we try to assess how those kind of ocean precursors affect the seasonal snowfall or summer precipitation. And then more likely, evaporation, I think evaporation would be not good target for us, but precipitation would be more related to ocean precasters. So, and then, yeah, that was our next step, what we want to try.
Are there more questions? Okay, maybe then I ask a question. Could you show the statistical model? It seems it has like these 3 predictors, right?
Oh, yeah, yeah.
And I've got a little, oh, okay. So the one is for -1 year, the other one is for -2 and -3 years. No, I think I get it now.
Yeah, but this is
So
only the beginning one, yeah.
Could you sort of quantify which of those 3 predictors is the most influential, most important ones? Or maybe I'm able to guess it. You tell me if that's wrong, all right? But I guess like the La Nina El Nino pattern is probably the most important one. But is that something you would agree with? Or okay, I mean, from those coefficients, you should be able to tell me, right?
Yeah, so it's pretty important question and pretty interesting question, because what we found is, so initially I believed La Nina would be important, so I include tropical Pacific. But what we found later is if we include tropical Pacific, scale is getting lower. So if we exclude tropical Pacific, so if we only use Atlantic and North Pacific, and that one is new forecast. And this is way higher scale compared to include the tropical Pacific. And also more longer.
So
And
why
then,
did you include the Pacific then, the tropical?
So, but this is consistent because in the coefficient it's also 1 order smaller in the tropical Pacific. And then maybe this is my kind of consideration. So tropical Pacific is more like ENSO variability, and the ENSO is more seasonal predictive skills. So if we include ENSO, that might be distract long-term low frequency variability. And then tropical Pacific, North Pacific and Atlantic, those are more lower frequency. And then, so if we only focus on this low frequency component, we may have more better skills and more longer. So, and then, yeah, so, but still, we don't know what is a decadal ENSO means. And then according to our inter-basin interaction concept, Atlantic contribute to more decadal-like ENSO. So if we increase Atlantic, we may kind of support or may increase some part of decadal ENSO component, and then they maybe contribute to the skills.
So if you contrast the statistical model skill with that from the dynamical model, which one is better?
So it's depends on the computational cost. I prefer dynamical model because it's more consistent, but it's super expensive to conduct.
But what
and the statistical model is cheap, right?
What about the skill value, the correlation?
Oh, correlation, yeah. So
which one is better?
Yeah, and then if read time, yeah, if read time is shorter, correlation becomes better.
Yeah, no, but if you use the statistical model for the same lead time and compare it with this dynamic outcome, is the dynamic model superior or not?
Good question, good question. Yeah, I need to overlay skills based on the statistical model. Yeah. Good question. Probably similar, I guess. Maybe. Yeah. Yeah, I didn't check. Yeah. I need to check.
Are there any other questions?
The chart in here. Here we go.
Yes, sorry.
I was just going to say, I wondered if you're familiar with the Erica Wise work. It was published in 2010, where she was looking at at the PDO and ENSO phases, and whether you're looking at positive and negative phase of those, and what the combination of them did to precipitation patterns. And she was primarily looking at sort of the north-south precipitation dipole in winter precipitation across the western US as a result of those. But I know in her paper she was looking at essentially looking at sea surface temperature or conditions for ENSO in the preceding summer between June and November, and then looking at winter precipitation the following year. And it seems like the area that you're looking at in the North Pacific somewhat correlates with PDO kind of area. And so I wonder with with PDO kinds of thing, it is a multi-decadal. And so maybe using an annual mean for those conditions in the North Pacific doesn't really matter, but using seasonal data in the tropical Pacific might be more important, and looking at season specific precipitation. I don't know, is there, not really a question there, it's more a comment. I guess.
Yeah, I agree. It's pretty important if you focus on the seasonal time scales. Probably ENSO is also one of the big component. And then many people suggest for the ENSO, I think probably it's consistent, but ENSO it might be related to more north-south or northwest, northeast, southeast kind of pattern. And then Colorado River region is kind of zero correlation, close to the zero correlation. So if focus on only the ENSO, signal is kind of unclear, particularly in this region around the Utah. But the point is there may be the time lag. And then again, so if we try simultaneous correlation, there's no signal in the tropical Pacific. But if it can 1 year later, 1 year time lag, we can see the La Nina-like pattern. So, and then Simon also suggested some like a decadal cycle of the ENSO and the causal decadal cycle, and that might be related to the Colorado River. So, so far I don't have any specific answer, but currently we are working different time scales, and then one of the point is there's a time lag between ocean mature phase and the response is a land, and that one makes complicated. So, but anyway, yeah.
Okay.
So,
I think we can continue after, but let me just say that thank you one more time. Officially, the seminar is finished now, and we can still discuss, but the official part of the seminar is over now. Okay, thank you, everybody.
Thanks, Thomas, and thanks everybody for coming.
Okay. So yeah, this is it's a lot of information, a lot of things going on, right? Yeah, so that SST contribution over the North Pacific, or let's say Japan or whatever that is, right? That's also interesting. Yeah, so I'm wondering, is this sort of, as the person before said, Zachary, I think said, that's maybe just a proxy for the PDO? I don't know, but I mean, one can probably look into the the power spectrum over that area of the SSTs and see whether this has sort of mostly the PDO signature or decadal variability in it.
Yeah, so it would be PDO. Yeah, and I saw one paper suggesting like a Kuroshio or Yashio, like a east coast of Japan, that sea surface temperature. That one also contribute to the precipitation over the United States through the dynamics, atmospheric dynamics. So there are a lot of debate.
So air-sea interaction over the Kuroshio extension has been studied. I know this from Niklas Schneider, for example.
Oh, yeah. Niklas,
right? And yeah, but when usually people think there is not that much sensitivity of extratropical SSTs. of the atmosphere to extratropical SSTs, but well, we don't know, right?
Yeah, and then recently my student, previous student, he graduated, he found Atlantic warming also contribute to the PDO. So, and then that one is not directly.
Okay. I remember vaguely there are papers who say something like this. Yeah. So inter-basin connectedness in ocean SST variability.
Exactly. So probably PDO have several components, not only one. Of course, ENSO is one of the driver, but probably there are another driver for the PDO. And then that one is still dynamically connection is kind of interesting for me. And then
I think now I understand also why your loading for the tropical Pacific is so low. And it's exactly as you said, I guess, because that's more on shorter time scales. There's not that much predictive, also out to 2 years or 1 year out from the ENSO signal. So you need longer variability, sort of PDO. And then you also suspected sort of that Atlantic transbasin or whatever you call it. That's also maybe an expression for decadal variability.
Yeah, so Atlantic prefer more low frequency. And then if go Pacific, ENSO is very dominated. And then everything just have an ENSO signal like more shorter, 5 years, 4 to 5 years per spectrum. So,
but if you would just take an index of the PDO and try to predict your stream flow, I mean,
yeah, true.
Could be easily tested, right? It's very simple.
Yeah. So I come at this. I'm in the geography department and come at this from a paleo.
From where are you? Are you from Utah State or from Utah University?
No. I'm here. I'm at University of Utah.
Oh, okay. Nice to meet you.
Yeah, you too. So I come at this from the paleoclimate side, and there's been a lot of work on the paleoclimate side, and I know there's I've seen a bunch of publications looking at I think it's again I'm as much geologist as I am a climatologist, maybe more so, but looking at precipitation anomalies across the U.S. When you're looking at phases of PDO, and then a number of people have looked at the AMO in conjunction with the PDO, and what patterns those get. And so I think there's quite a lot of work that has been done doing exactly what you're trying to do, but most of it that I'm familiar with anyway is trying to understand paleoclimate signals, not forecasting forward. Right. I mean, that might be something, if you're not familiar with that literature, it might be worth digging into, because there are a lot of people that have dug in and looked at all these correlations between, certainly the precipitation and the drought indexes and these various indices, right?
Yeah. So if you can share with me some like a difference, it would be also great.
Yeah.
So when you say paleo, how far do you go back? Is it sort of reconstruction of the stream flow of the Colorado over the past couple hundred years, something like that?
So I haven't worked in the Colorado Basin, but there's definitely a lot of work that's been done on the Colorado Basin using tree rings to reconstruct stream flow. So folks like Connie Woodhouse, have done that.
So these are a couple of 100 years going on.
In that case, they've gone back, I think, 1,500 years.
Okay.
My research, I've worked in the Bear River Basin, and I was looking at speleothem and lake records. So the resolution isn't as high to do stream flow, right? I mean, the resolution I'm looking at is, multi-decadal kinds of resolution, not something that you could predict on a year-to-year basis. but certainly I definitely saw in my work, I did the same thing where I was using SNOWTEL data in my site and climate composites and was able to see a very strong correlation with PDO. Interestingly, not so much on the extreme drought years, but definitely on the really wet years in the Bear River Basin. There's some, and there's definitely good correlation with dry years too, but it was even better on the wet years. So yeah. So yeah, it's very interesting. And I'm, I think what you're working on is probably more practical. People care more about being able to forecast forward than understanding going back. But there's a lot of overlapping research, I think.
Yeah, sure. Particularly for the paleo reconstruction, they have more longer history, right? So we can more statistical significant signal.
Yeah.
So
yeah.
It's really great.
There's one of Justin DeRose. I don't know, he's there.
Justin, yeah.
Yeah, he's there at Utah State, and he's done a fair bit of the tree ring based stream flow reconstruction. So I'm sure he's familiar with a lot of these paleo reconstructions as well. Yeah.
Yeah, sure. And then Simon, one of my colleagues, he also worked with Justin. So
okay.
Again, yeah. There's another kind of opportunity to go back more.
Yeah.
Modeling side is kind of tricky. So, but still, we can kind of merge our concept and then, but PDO and then tropical Atlantic is kind of, tropical Atlantic it sounds like new for me. And then it's really far away and then, but still important. And they're getting better understanding of dynamics. So, yeah, a lot of work.
Yeah. Well, and the other pattern I know that popped up, and it's less. I understand the drivers behind it less is, and it's kind of larger scale, but it pops up a lot in the paleo literature. It's called the Pacific North America pattern. That kind of creates an east-west precip gradient across the continental U.S. But I found, in my own research, again, looking kind of more north, that the persistence of the PNA, it definitely seems to control the position of the storm tracks, which then really controlled how much winter precip, we certainly ended up getting. So that may also be, that if that pattern's in place, I would suspect that you'd see drought pattern in the Colorado Basin. Whereas if it breaks down, then probably not.
Yeah, and so my colleague also say, my one student analyzing, before 1980, PNA pattern is dominated, but after 1980, pattern is